As we continue our look at these trigonometric integrals, we are going to take a pit stop. Right? And this pit stop will involve looking more closely at the powers of the secant function. You might wonder, why are we looking specifically at this one? Well, of all the trig functions that we need to know how to integrate and all their powers, it just turns out that the powers of secant are deceptively tricky, right? So tricky that we're going to end up deriving a formula that allows us to reduce the integrals that involve larger powers of secant into smaller powers of secant. So what we have to be able to do, we have to ensure that we can at least integrate like secant x and secant squared, and then this formula becomes very, very effective. All right, and once you see the process, you'll see exactly what I'm referring to. So before we start deriving this formula, let's actually make sure that we remember our the antiderivatives of secant and secant squared, right? Now previously we established this antiderivative. So if we look at the antiderivative of secant x, well, we know that that's the natural log of the absolute value of secant x plus tangent x plus c, right? We derived this one in a manner that's somewhat similar to how we derived the antiderivative of tangent, right? And now this is one that we, if needed, we can just simply state, right? What about secant squared? Well, that one is like a underhanded pitch, to a baseball, a professional baseball player. They're just going to hit this one out of the park, because this is one of our standard results from Calc 1, because we know that the derivative of tangent is secant squared. Therefore, the antiderivative of secant squared is the tangent function, right? So there we go. So at least we know how to integrate secant x and secant squared x. So then the question is, what happens when this power is 3 or greater, right? What happens if we have something like this? So now what we're going to do is consider integrals of this form, right? Where n is an integer that's greater than 2, right? So where n is greater than 2 and is an integer. So for instance, like, what is the antiderivative of secant cubed, or secant to the 4th power, so forth, all right? Well, it turns out we can do a few tricks, right? So we're going to pull out a couple tricks out of our integration bag here, and derive a pretty nice relationship in the end for this type of integral. And the relationship, it will relate this integral with ones that involve smaller powers of secant. In fact, these two right here, right? So the first thing we're going to do, since n is an integer that's greater than 2, I can factor secant to the nth power like this. So this is equal to secant to the n minus 2 power, right, times secant squared, right? So if I make sure that n is big enough, right, even if I subtract 2 from it, I'll still have a nice positive integer here. And what I'm doing is I'm writing this special factor kind of off to the side, right? So again, we can see that this product here is equal to the secant of n. Why is it equal? Because if we were to multiply these two and add the powers, right, n minus 2 plus 2 will be equal to n. right? Again, it seems like a strange thing to do. The next thing is going to seem even stranger. What we're going to do is apply integration by parts to this, right? Now, when you look at this, you're like, well, these are both trig functions. How am I going to choose? Well, this is one of those rare instances where Lie doesn't really give you a definitive answer as far as your choice, right? But remember, we choose our u in such a way that it's easy to differentiate, and we choose our dv in such a way that it's easy to integrate. Right? Well, look at what we have up here. We have a fairly simple integral for secant squared. And since I have a secant squared here, I am going to choose this as my dv because it's relatively easy to integrate. And then by default now, this would have to be my u. So you can see just the way we make our choice is a little bit different than all the other integration by parts examples that we did, right? It's no less valid, it's just different, right? So let's write this down and see what happens. So we're going to let u be equal to this expression. So secant of x to the power n minus 2. And again, this is a nice positive integer. And then we're going to let dv be equal to secant squared of x dx, right? So let's do the easier one. Let's go ahead and integrate this. Let's find our v. So v, as we know, is tangent of x, right? du here, we're going to have to use our power rule along with our chain rule, because since we have a nice positive exponent right there, we think of, so this is actually saying secant of x raised to the power n minus 2. So we can see that the chain rule is in effect. So what I can do is start by differentiating the power. So when I go to write down my du, bring the power down, so that's the quantity n minus 2, and subtract 1 from this power. Well, if I subtract 1 from n minus 2, I am going to have n minus 3, right? So we have that part. But then the chain rule says I have to multiply by the derivative of what's inside. Well, the derivative of secant is secant x tangent x, right? So look at what we have here. We have secant raised to the power n minus 3 times a factor of secant that's raised to the first power. So when we add those powers, here is where we end up, right? Oh, I didn't write my dx here. Let's put the dx. So du is a quantity n minus 2, and then this product here is secant to the power n minus 2 of x, and then I have a factor of tangent here, so tangent x dx, right? So that's my du, right? So here's our v, here's our du. So now let's apply what our integration by parts formula says. So this integral, so n minus 2 of x, and then times secant squared of x dx, that's equal to u times v, right? So I have my tangent times secant of x to the n minus 2, right? So I'll put let's say we put the tangent function first, and then we have secant to the power n minus 2 of x, and then the rest of the formula is minus the integral of v times du. So I have to multiply this function and this differential. But when I multiply these two, I have two factors of tangent, so that will give me tangent squared. So I still have my n minus 2. I still have my funny expression here for secant, but then I'll have a tangent squared, and then I'll have my dx. So let's write that down. So we have n minus 2, and then secant to the n minus 2 of x, and then I have a tangent squared of x, and then times dx. Right? Now, the n minus 2, that is this n minus 2 is a constant, so we can pull that out, right? Again, remember we're saying that n is some integer. We don't know what integer it is. It's just an integer that's bigger than 2. So let's factor out the n minus 2. So we have our tangent of x times the secant to the power n minus 2. Factor out the n minus 2, so we have this, and then inside the integral now, what I'm going to do is make use of another version of our Pythagorean identity, right? In fact, let me take a couple seconds just to show you, the different versions of that identity. So we know this one. This is the most, I would say, popular, maybe most commonly used one. If I take this identity and I divide everything by cosine squared, so if I divide each term, these three terms, by cosine squared, what do I get? Well, sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. So actually what I am able to do, since I have since I have everything in terms of secant on this side, I'm going to try to do the same and try to get this side in terms of secant as well. So that means I would have to replace tangent squared with this. So if I solve this equation for tangent squared, I will get secant squared minus 1. So let's take this and replace tangent squared. All right, let's see what happens. So then so now I'm going to replace tangent squared x with this quantity. I have secant squared x minus 1, and then times dx. All right. Okay, so again, what we're trying to do is to keep all the integrals solely in terms of powers of secant, right? That's the easiest way in order to get to this special formula, right? And we have a little bit of work to do, but we're getting closer. So I write all of this down. Now, if we look at this integrand, if I distribute the secant to the n minus 2 power, so if I multiply these two, when I add the powers, look what I get back. I get back secant to the nth power. And then over here, when I distribute it to the 1, I'm going to get, or minus 1, I'll get minus secant to the n minus 2 power, right? dx. All right. So again, what does this mean? Well, we're getting there. Now, if we go back to this original integral and combine these two to where it was in the beginning of this process, if I add these two exponents, I end up also with an n, right? If I have n minus 2 plus 2, I'm left with n. So therefore, here, this was our original integral. So it's not surprising that we can write it back in this form. And then here we have this product that came as a result of integration by parts. Like that. And now what I'm going to do here is let's use our properties of the definite integral and split this into two separate integrals, where one is the integral of secant to the nth power, and then minus the integral of secant to the n minus 2 power, right? Now, they're both going to be multiplied by this, so let's write this down carefully. So if I split this into two indefinite integrals, it will look like this. The integral of secant to the nth power with respect to x, and then minus the integral of secant to the n minus 2 power with respect to x, right? And then if I distribute the quantity negative n minus 2, multiply this integral and this integral, this is what happens. So we have the integral of secant to the nth power with respect to x. Here's our tangent of x, secant to the n minus 2 power. Now distribute this constant to the first one, so it just ends up being negative n minus 2, or sorry, the negative of the quantity n minus 2 times the integral of secant to the nth power dx. And again, if I take this constant and multiply the second integral, then that negative and this negative make the product a positive n minus 2 times the integral of secant to the n minus 2 power with respect to x. All right. So again, what have we done? Well, look carefully. The integral that we started with right here is also on this side of the equation, but it has an extra constant in front. So this integral and this integral are exactly the same. So what I can do, if you remember, we encountered this before when we were doing some of those integration by parts problems where we had to use a little bit of algebra at the end to simplify and get our answer. Well, here what we're going to do is use the same type of algebra to simplify and get this specific type of formula that we will need, right? So what I'm going to do is take this term and move it over to the left. And when I do that, this sign will become a positive sign, right? So let's do that. So I'm going to, in fact, well, actually, let me do this first. So let's take our secant to the nth power, bring that down, move this across the equal sign, and it becomes plus n minus 2 times the integral of secant to the nth power dx. And then we have our equal sign, bring this down. So we have tangent of x secant to the n minus 2 power. And then we have this other integral here, so plus n minus 2 times the integral of secant to the n minus 2 power. All right. Now, again, it doesn't look like a lot, but we're getting close because this is what's going to happen. Because these two integrals are exactly the same, this one has a coefficient of 1, this one has a coefficient of n minus 2, I can add the coefficients together and combine this into one term. It's just like taking, for instance, 1 times x, or maybe I shouldn't use x, let's say 1 times t plus n minus 2 times t. So you add the coefficients when you're adding like terms. These are like integrals, so you add the coefficients. So if I take 1 and I add n minus 2, I'm going to end up with n minus 1. So if I add these coefficients, 1 plus n minus 2, that's n minus 1. And that coefficient now is in front of the secant to the nth power integral. So I have n minus 1 times secant to the nth power, that antiderivative on that side. And then over here, what do I have left? Well, I pretty much have the same thing. Tangent x times the secant to the n minus 2 power, and then plus n minus 2, and then times secant to the n minus 2 power, right? And then what we're able to do now is isolate the integral that we started with by dividing all three terms, right, by n minus 1, right? So let's do that. So dividing this by n minus 1, this by n minus 1, and this by n minus 1, we end up with this very useful formula for reducing the powers of secant, right? So if I have the integral of secant to the nth power, then that's equal to, and let me write it this way, 1 over n minus 1 times this first term on the right hand side. So tangent x secant to the n minus 2, and then plus, and then I also have to divide this term, so I'm going to divide this constant n minus 2. This is one term, so if I put the whole thing over n minus 1, it's the same as putting the n minus 1 in front of the integral, like this. And then we have the remaining integral right here. All right, and it might not look like much, but this is the reduction formula for powers of secant. Whew. Right, I feel like we need a yoga break after something like that, right? So what do we do with this? How do we use it? Well, let me illustrate. So again, I'm going to go back and write down what we know about the antiderivative of powers of secant. So for instance, again, I know that the antiderivative of secant x dx is the natural log of the absolute value of secant x plus tangent x plus c. And I also know that the integral of secant squared x dx is tangent x plus c. So earlier we asked, well, what would it look like, or what is the antiderivative of secant cubed? So now if I have the integral of secant cubed of x dx, what I can do is I can apply this reduction of order formula and reduce it, because if you notice, the power of the secant that's on the left hand side is greater than the power of the secant on the right hand side. So by applying this formula, and it is what we call a recursive formula, right? What we're able to do is to take this integral that involves a larger power of secant and break it down, reduce it to one that has a smaller power. And then you can repeatedly use this till eventually you bring all of those integrals back down to something like this. All right, so we'll just do a few examples to illustrate how it works. So in this case, my n is 3. So I start with an n of 3 on this side. So wherever there is an n on the right hand side, just replace it with 3, right? So because in this case n is equal to 3, so my reduction formula tells me to do this: 1 over 3 minus 1 times the tangent of x raised to the, now again, when n is equal to 3, when you subtract 2, you're just left with the power of 1. So we have that. And then plus, again, when n is equal to 3, this numerator is 1. This denominator is 2. And then we have times, and then again, if n is equal to 3, then this exponent breaks down or reduces to 1. So we have this, right? But we know what the antiderivative of secant is. It's this, right? So when we put it all together, here is our result for secant cubed. It's 1/2 tangent x times secant x. So we have 1/2 times tangent of x times the secant of x plus another 1/2, right? But now it's times the antiderivative of secant, which is our ln of the absolute value of secant x plus tangent x, right? Let's make sure we have enough room to write that all down. So we have the 1/2. So now I'm gonna write down what this is equal to. The ln of the absolute value of secant x plus tangent x plus c, right? And so this is the antiderivative of secant cubed, right? Well, what does it look like for secant to the 4th power, right? Well, now that we know what the antiderivative of secant cubed is, well, I should be able to use my reduction formula again and reduce the secant to the 4th power down to one of our simpler ones, right? So let's see what happens. So we have the integral of secant to the 4th power. And for this one now, my n is 4. Right? So I'm going to go back to my reduction of order formula, and wherever there is an n, now replace it with 4. So we're going to have 1 over 4 minus 1 times the tangent of x times secant to the 4 minus 2 plus 4 minus 2 over 4 minus 1 times the integral of now secant. But again, in fact, let me just plug it in without any simplifying. Let me just plug all the, replace all the n's with the number 4 so you can see what this reduction formula tells me. And you can see what happens over here to that power of secant, right? So if we, now let's kind of simplify this. So this will be 1/3, and then I'll have tangent x to the secant squared, right? Or secant squared. So like that. And then plus, and then this is 2/3 times the integral of secant squared. But we know the integral of secant squared. Again, that's why we establish these simpler results, so that when they pop up in our reduction formula, we know exactly what they are. So the antiderivative of secant squared is tangent x. So now we can actually write down the antiderivative of secant to the 4th power, right? So yeah, we should be able to get it on this line. So it's 1/3 times the tangent of x times secant squared plus, and now it's 2/3 times tangent x plus c, because this antiderivative is tangent. And that's actually this is one of the few ones in this process that we can go all the way back to Calc 1 and say, yep, I know that the derivative of tangent is secant squared, so the antiderivative of secant squared will be tangent, right? So here's the final answer for the antiderivative of secant to the fourth power. 2/3 tangent x plus c, right? So it turns out that, again, this procedure, now once we know so you see quite quickly, right? I mean, obviously it took us a while to derive this formula, but once we have this formula, it quite easily can be applied to larger and larger powers of secant. But what you want to do, you want to make sure that you have these, the lesser powers written down. So that, for instance, if I were to do, let's do one more just to see what it looks like. Let's see what it looks like if we did secant to the fifth power, right? So we have secant to the fifth power. Well, in that case, my n is equal to 5. So let's see. So let me see if we can do it by memory. Or basically, I mean, we can look at this part of it and we can see the pattern. So it's 1 over 5 minus 1 times the tangent of x times the secant of 5 minus 2, or to the 5 minus 2 power, and then plus 5 minus 2 over 5 minus 1 times the integral of secant to the 5 minus 2 power with respect to x, right? So again, this is always the standard way. Whatever your n is, you replace that n with that specific number, and then you see what power of secant you're left with. And it's never really a surprise. It's always going to be 2 less than this power that we started with, right? So we're going to reduce secant to the fifth power to secant to the third power. But look, we know what secant to the third power is. So we get to use that for later on, right? So let's write it down. So this is now 1/4 tangent of x times secant cubed plus 3 over 4, and then this is secant cubed. Well, let's write down what the antiderivative of secant cubed is. It's all of this. Now it's 3/4 times all of this. So I'm going to use square brackets, and then we have 1/2 tangent x secant x plus 1/2 times the natural log of the absolute value of secant x plus tangent x plus c. So again, I'll put it all in the square brackets because technically even the constant is going to be multiplied by the 3/4, but we know that's not going to change the fact that it's a constant. So here's the antiderivative of secant to the fifth power. We have 1/4 times the tangent of x secant cubed, and now plus, distribute the 3/4, we'll have 3/8 times the tangent of x times the secant of x, and again distribute the 3/4, we get another 3/8, so 3/8 times the natural log of the absolute value of secant x plus tangent x, and then close the absolute value, and then this is technically like a C1, so I'll just go ahead and relabel it. So there is still my constant of integration, right? So that's the reduction of order formula. Let me scroll back up so we can sort of take one last look at it, because we did a lot of work to get to this, right? And obviously this is something that you want to have handy whenever you end up with just powers of secant, right? You want to have this, and at the very least, you want to have the first two here. Now, depending on how big this power is, we might have to apply this formula, like I said, recursively a few iterations to finally break it down to where we have all the integrals evaluated. So for instance, if this were a 10, then we would have to break it down to a power of 8 on this side. But then if I don't know what secant, the antiderivative of secant to the 8th power is, then I'd have to use my reduction formula again and break that 8th power of secant down to the 6th power of secant. And then that 6th power of secant will get broken down to the 4th power of secant. And then, so we know what the antiderivative of secant to the 4th power, we did that. But let's say we hadn't done that. Then we would have to break this further down to the antiderivative of secant squared, right? So at the very least, you can reduce the integral of any integer power of secant to either this or this. If it's an odd power, a large odd power, it will eventually come down to secant to the 1st power. If it's a large even power, then eventually it will break down to the integral of secant squared. So at least that guarantee is good. It's just that, there's some tedium as far as breaking it down in this recursive fashion, right? And we will see in not so distant future where this result now plays a key role in another part of a process, right? So it's like we're just building and building all these different tools to have them at our disposal whenever needed. All right, well, if you want to see how that works, tune into the next video. See you then.